Assalamu alaikum. So inshallah today I'm continuing the revision with the chapter 5. Revision in chapter 5, which is related mainly to the application of the first law of thermodynamics for open system. So we do have two cases: open system is steady flow, and we do have the case when we do have unsteady open system on a steady flow. A steady flow, like most of the engineering devices, are steady flow devices, including turbine, compressor, pump, nozzle, diffuser, and so on. We do have many steady flow devices. On a steady flow, all actually the processes for open system will be considered as a steady flow unless we do have a charging or discharging, or discharging processes. In those processes, we do have either a tank to be filled with a certain fluid, or we do have, when we do have a tank and this tank is discharging the flow, or when we do have leakage inside the tank or something. This is the case of unsteady flow. Now let's consider the first case when we do have a steady flow open system. As we said, in this case, the system is open, so in this case it allows for both mass transfer and also for energy transfer. And based on that, we'll do have two equations: the energy equation, which is the first law of thermodynamics for open system, in addition to another equation, which is the mass equation or the continuity equation. So let's consider a steady flow open system. When we do have a steady flow, so let's start with the mass equation or the continuity equation of the system. The general equation will just tell summation of mass inlet to the system equal to summation of m dot exit out of this system. M dot is the rate of mass flow rate, which is calculated in kilogram per second. This summation indicates actually when we do have a system with more than one inlet and more than one outlet. Okay, so in some system we do have more than one inlet to the system, so we'll just summate actually this inlet mass flow rate m dot 1, m dot 2 plus m dot 3. In case of a steady flow, this should equal to the summation of mass outlet, which is m dot, let's say, 4 plus m dot 5. So this is the case when we do have a steady flow. Summation of mass flow rate inlet to the system is equal to summation of mass flow rate out of this system. Right? In case of we do have single stream, only we do have single stream, and this is actually the case of most of the engineering devices like turbine, compressor, nozzle. Only we do have a single inlet stream and single leaving stream. So in this case, we can just remove this summation. So in this case, we can say actually m dot inlet to the system is equal to m dot exit out of this system. Type this m dot is the mass flow rate is equal to density multiplied by area multiplied by velocity. So as it at inlet is the same as at outlet, so just replace inlet and outlet with 1 and 2. So we can say rho 1 A1 V1, which are the condition at the inlet section, are equal to rho 2, which is the density at the exit section A2 multiplied by the velocity V2. Area multiplied by the velocity is called the volumetric flow rate V dot. So the mass flow rate, here is the mass flow rate M dot, will equal to the mass flow rate inlet, same as mass flow rate at outlet, equal to density multiplied by the volumetric flow rate. V dot is the volumetric flow rate calculated in meter cube per second, because in some cases maybe the volumetric flow rate is given for a system, and we can calculate the density so that we can calculate the mass flow rate. Density, as you know, is equal to 1 over specific volume. So if the working fluid is a steam, like if we do have a steam turbine or something, so in this case in the table we have to use a steam table, but the table does not contain density. Just we do have the table, in the table the value of a specific volume. So density is equal to 1 over a specific volume, then we can substitute in the mass equation to calculate the mass flow rate or the volumetric flow rate. This is in case if we do have a single stream. But in case if we do have incompressible fluid, incompressible substance may be solid, not fluid, maybe actually solid or liquid. So in this case, for incompressible substance, density, which is 1 over a specific volume, in this case is constant. So in this case, m dot will equal to density rho 1 A1 V1, which is the same as rho 2 A2 V2, which is equal to rho multiplied by V dot. Again, we're just repeating, so density is constant, so rho 1 is the same as rho 2 is the same as density, so in this case the volumetric flow rate is the same, equal to A1 multiplied by the velocity V1, and it is the same as A2 multiplied by the velocity at the exit section V2. So in some cases maybe the volumetric flow rate is given, and in case of we are considering the flow as incompressible, so the density in this case will be constant. So we can say the volumetric flow rate at inlet is the same as at outlet. But actually the general case when the flow is not incompressible, the general cases apply because the volumetric flow rate at inlet is not the same as at outlet. This can be the same only if we do have the same density in this case. And this is regarding the mass equation. As we said, the mass equation is summation. This is a general case. M dot N equal to summation of M dot outlet. We have reduced the case for single stream. We can remove this summation. And we have reduced the case for a special case when we do have incompressible flow. Type, we do have the second equation, which is the first law of thermodynamics for an open system. And just here also, I will not be telling from where we can just, we have reduced this equation, just I will write down this equation. So the rate of heat transfer minus the rate of work transfer is equal to summation of M dot exit multiplied by H exit plus V exit squared divided by 2 plus J multiplied by Z exit minus summation of M dot inlet multiplied by H inlet plus V inlet squared divided by 2 plus J multiplied by Z inlet. And this is actually the general form of the first law of thermodynamics for a steady flow open system. Q is the heat transfer, work, rate of heat transfer, work, W dot is the rate of work done. This should be measured or calculated in kilowatt. Same, this term should be in kilowatt, mass flow rate in kilogram per second. All of these terms actually should be in kilojoule per kilogram, but this term to be in kilojoule per kilogram we have to divide by 10 to the power 3. Please don't forget this, to have the same sign for the same unit for all terms. You have to divide those terms by 10 to the power 3 so that the unit will be also kilojoule per kilogram. And in this case the rate of work done or rate of heat transfer will be calculated in kilowatt in this case. But in case if we do have single stream, like when we do have a nozzle, turbine, compressor, all of these devices we do have only single stream, so we can remove just this summation and we do have a steady flow, so M dot inlet is the same as M dot outlet, so we can take it as common. So the first law will be Q dot minus work dot equal to M dot multiplied by H exit minus H inlet plus V exit square minus V inlet square divided by 2 plus G multiplied by Z exit minus Z exit minus Z. And this is actually the equation when we do have single stream steady flow open system, considering a single stream flow like the case of we do have a turbine or compressor. So this will be the case. As I said again, we have to divide here by 10 to the power 3, divide here by 10 to the power 3, so that we can keep the same unit through the whole equation. Actually those terms, we can just actually consider each of this term and see how we can substitute in this term and when we can actually neglect any of those terms. Let's consider term by term on this equation so that actually we are able to reduce this equation in the exam and we can also solve any problem. And here is the equation again, is rewritten again for steady flow open system considering single stream. So it will be Q dot minus work dot equal to M dot multiplied by H exit minus H inlet plus H change in kinetic plus H change in potential energy. This term again we have to apply sign conversion. It should be positive when it is added to the system, and it should be negative, substituted with negative sign when it is rejected from the system, and it can be 0, as I said also before, when you do have an adiabatic system, insulated or isolated system, or if not given or required. So if not given or required, so in this case also we can consider the heat transfer to be equal to 0. Like for the reverse of this, the sign conversion for the work, it will be positive if it is produced by the system, like in case if we do have like a turbine or something. It should be negative when the system is consuming work, like if we do have a compressor or pump or any other device that is consuming work in this case. So the sign of the work in this case should be substituted with the negative sign. The values of each exit and each inlet depending on the working fluid. If it is steam, we can just use a steam table. Refrigerant, we can just use the refrigeration table. If it is air, we can use air table. For variable specific heat analysis, table A17. If it is air or other fluid, you can use actually A17 up to A25. Or for constant specific heat analysis, we can just use delta H is equal to CP average delta T, and CP average is calculated from table A to B. So depending on the working fluid, we can calculate H exit minus H inlet. Those two terms actually will be neglected or equal to 0 if not given or required. So if not given or required, we'll just be neglecting those terms. Usually most of the cases this term regarding potential energy will be neglected, but actually this term may not be actually given, but in some cases he may give you area A1 and area A2 are given in this case, and mass flow rate also is given, M0 is given. So in this case, can we calculate velocity V inlet and V exit? So in this case we can just say M0 equal to rho 1, inlet let's say 1, A1, V1, exit is 2, A2, V2 equal to M0. In this case we do have mass flow rate is given, and in this case we can calculate also the density. This term is equal to density multiplied by the volumetric flow rate. And density, as we said, is 1 over a specific volume, which we can get from the table if the working fluid is steam. Volumetric flow rate may be given, then we have the mass flow rate. Then at condition 1, we can get the density rho 1, which is 1 over specific volume V1. And we do have area 1 and area 2, then we can calculate using the mass equation. In this case, we can calculate the velocity V1 and V2, and then we can substitute. So this term will be neglected, kinetic energy, if not given or required, and also if area A1, cross-sectional area at inlet and exit are not given also. So if they are not given, we can consider it as 0. Cross-sectional areas are given at inlet and outlet, so in this case mass flow rate or volumetric flow rate will be given. Then in this case we can just calculate the velocity V1 and V2 using the mass equation. This term regarding potential energy, in most of the cases this term will be neglected. In some cases, actually, in some problems, they require the solution to calculate the heat transfer or the work actually per unit mass flow rate. So just let's divide this equation to get the specific form of the first law of thermodynamic equation per unit mass flow rate. So in this case, Q minus work will equal to the change in kinetic energy, the change of enthalpy plus a change in kinetic energy plus a change in potential energy. And in this case, the heat transfer and work are calculated in kilojoule per kilogram. All of these terms should be in kilojoule per kilogram. Okay, so this is the reduced equation per unit mass flow rate. Let's start actually with some steady flow devices, starting with turbine and compressor. So in case of, let's say, turbines, the idea of the turbine, we do have an expansion process through the turbine. So turbine, usually the flow is coming to the turbine at pressure P1, temperature T1, which is high pressure and high temperature. And then the flow expands through the turbine to drive the shaft and then we can have actually work out of the system, and the flow is leaving at pressure B2 less than B1 and T2 is less than T1. So the process through the turbine is expansion. The reverse of this actually is through the compressor. The flow comes to the compressor at low pressure B1, low temperature T1, and the function of the compressor is to increase the pressure, and also as a result the temperature will be also increasing. And based on that, the compressor consumes actual work. So we do have input work to the compressor. In those two cases, we do have single stream, single flow inlet, single stream at inlet, and single stream at outlet. So we can just apply this equation, which is the first law of thermodynamics for an open system single stream. Okay, it will be just the same equation, Q minus work equal to M multiplied by delta H plus a change in kinetic plus a change in potential energy. And the same actually is applied, same case is applied when we do have actually this term, if not given or required, will be neglected. This term also in most of the cases will be neglected if not given. And this term Hx minus H inlet in case of turbine, most probably in this course we are dealing with a steam turbine. So in this case the condition at inlet and exit will be given, so you can use a steam table to calculate H exit and H inlet. Mass flow rate should be given or required. In some cases, and most probably the case of turbine and the compressor, we neglect the heat transfer, so it may be adiabatic, but in some cases they may give you actually this heat transfer. If it is given, then we can just consider it. Usually we do have some heat is lost from them, so in this case we have to substitute this heat with negative sign. In case of compressor, if the work is required to be calculated, just leave the sign as is, and the final result, in case of compressor, they will find this value as negative, indicating compressor is consuming work. If it is to turbine, the final value will be positive, indicating actually the system is producing work. In case of the working fluid, let's say is air in case of a compressor. So in this case, we do have for ideal gases, we do have two cases. One case is constant specific heat analysis, so we'll say delta H is equal to CD average multiplied by delta T. The second case, which is a variable specific heat analysis, in this case we can calculate just the delta H from table A17. If not air, we do have table from A17 to A25, then we can also be using this table to calculate H exit minus H inlet. You can look at the example in the slide about the case of compressor and turbine. But let's consider another special case, which is the case of nozzle and diffuser. In case of nozzle, the function of the nozzle, we do have flow coming to this nozzle. The area is contracted in the flow direction, so the velocity V2 at the exit is increased. V2 is much greater than V1, and based on that B2 is reduced, should be much less than B1 at the inlet section. Let's say this is the inlet section 1 and this is the exit section S2. This is the case when we do have nozzle. When we do have a diffuser, the case is reversed. We do have the flow is coming, but the area is increasing in the flow direction, so the velocity V2 is much less than V1, but the pressure build up through the system, so pressure V2 is much greater than V1, and in this case the system is called as diffuser. Due to the small dimension of nozzle and diffuser, we consider the heat transfer Q is equal to 0. Usually we neglect the heat transfer. And for those systems, we do have the two systems, the work also is equal to 0. From the inlet to the exit section, we do have the same elevation, Z1 is the same as Z2 in most cases. So we don't have a change in potential energy. So we don't have heat transfer, we don't have work, we do have single stream flow. So this term will be, those two terms will be 0. Potential energy, we don't have a change. For the case of nozzle and diffuser, so in this case, we do have H inlet or H1 minus H2 will equal to V2 square minus V1 square divided by 2, and you have to divide by 10 to the power 3. And this is the energy equation when we do have nozzle or diffuser. The equation will be reduced to enthalpy at inlet minus enthalpy at outlet equal to V2 square minus V1 square divided by 2. And in case actually of nozzle, the term V1, velocity V2 is much greater than V1, so we can neglect the V1 for nozzle. And for the diffuser, V2 also can be neglected. V2 can be neglected for the diffuser in case of the diffuser as the velocity V2 is much less than V1. And in both cases for nozzle and diffuser, we do have another equation which is mass equation, which is mot equal to ρ1 K1 V1 is the same as ρ2 A2 multiplied by V2, which is density multiplied by the volumetric fluid. So those are the two equations in case of we do have nozzle, or diffuser. Okay. Right, let's continue with the devices. We do have also, in case of we do have mixing chamber, heat exchanger, and general flow and pylon duct. And devices will be done with a steady flow device, and we will be left with the case of unsteady flow. Right, let's consider this in case of mixing chamber. Let's continue the devices. So number 3, steady flow devices, considering the throttling valve. Just a throttling valve is called also as capillary tube. It's called also as, in case we do have porous plug, or when we do have adjustable valve. All of this actually means we do have the case of throttling valve. So the idea of the throttling valve, we do have the flow is just in a very small area, so that actually we do have high amount of pressure losses within the system. So the pressure will be reduced, and also the temperature will be reduced. So this is the valve, and the flow is forced to go actually in a very small area. So let's say this is cross section number 1 before the valve, and this is cross section number 2. Between cross section 1 and 2, we do have the same cross section area after the tube, so the flow will build up again, will attain the same velocity. So V1, the velocity V1 is the same as velocity V2, the elevation Z1 is the same as the elevation at the outlet section Z2. Usually through this valve we don't have any heat losses, and also we don't have work. If you reduce the energy equation in this case, so you will result actually with the enthalpy at inlet H1 is the same as the enthalpy at outlet, or we can say enthalpy is internal energy plus P1 specific volume B1 equal to U2 plus B2 multiplied by specific volume B2. And the same mass equation is applied. M about ρ1 A1 B1 is the same ρ2 A2 V2 equal to the density multiplied by the volumetric fluid, and this is the mass equation. So this is the energy equation, and this is the mass equation in case of we do have a throttling valve. In case we do have a mixing chamber, let's say this is device 4. Mixing chamber, we do have usually the most common case is the shower. When we do have mixing chamber, we do have hot fluid is being mixed with a cold fluid. But this is one case. We may have the general case when we do have actually 2, 3, 4, 5 fluids are being mixed, and we do have single stream is leaving, let's say, at cross section 3. And maybe also we do have more than one outlet. It's okay. So whatever number of inlet, whatever the number of outlet, in this case we do have heat exchange inside, but externally we don't have heat transfer, so Q is 0. In this case also the work is 0. We do have the change in kinetic energy is neglected, change in potential energy is also neglected. So if you look at the mass equation, but still the system is a steady flow, so summation of M dot inlet equal to summation of M dot exit, or we can say M dot 1 in this case plus M dot 2 equal to M dot 3. This is the mass equation in this case. And it can be applied also when we do have, let's say, 3 inlets, so m dot 1 plus m dot 2 plus m dot 3 plus m dot 4 plus any number of mass flow rate at inlet is the same also the mass flow rate at outlet with any number. So in this case we do have 2 inlet and 1 outlet, so it's okay. The energy equation in this case, we can just reduce it when we don't have a changing kinetic changing potential, we don't have heat transfer, we don't have work, so we result with summation of m dot inlet multiplied by h inlet equal to summation of m dot exit multiplied by h exit. In this case, for this example, so it will be m dot 1 h1 plus m dot 2 h2 m dot 3 equal to m dot 3 multiplied by h3. So if you do have a steam and refrigerant at point 1, so the condition will be given at point 1, P1, T1. So in this case, we can just go to the table, get the enthalpy H1. Also at point 2, B2, T2, maybe steam or something for water. So at B2, T2, then in this case, we can calculate H3. And also at point 3, we will have P3, T3, then we can calculate H3. Most probably in most of the cases, we will neglect the pressure drop. So usually P3 is the same as B1 and also is the same as B2. This is the case if we do have a mixing chamber. A very similar case when we do have heat exchanger. This is case 5. Heat exchanger also is a mixing, can be considered like a mixing chamber, but actually the fluids are not mixed. We do have heat transfer also between the hot and the cold fluid, but we don't have mixing. So in this case, let's say we do have hot fluid coming through inside this pipe, coming at point 1 and leaving at point 2. And the cold fluid, let's say, in the shell side will be coming at point 3 and leaving at point 4. Usually, if we consider the whole system, we do have internal heat transfer from the hot fluid in the tube to the surrounding cold fluid, but externally we don't have heat transfer. This is most probably, but we may have heat transfer externally. In this case, we don't have also work, and the change in potential energy equal to the change in kinetic energy is neglected equal to 0. So in this case, the equation will be reduced also. Okay, so down here, the mass equation will be reduced to summation of m dot inlet equal to summation of m dot exit. But in this case, we don't have mixing. So in this case, we can say m dot 1 equal to m dot 2 equal to mass flow rate, let's say, of the hot fluid, m dot 1. And m dot 3 is the same as m dot 4, let's call it m dot c, which is m dot of the cold fluid. This is the mass equation. And the energy equation will be reduced to same summation of m dot inlet h inlet equal to summation of m dot exit h exit, so m dot 1 h1 plus m dot 3 h3 equal to exit m dot 2 h2 plus m dot 4 multiplied by h4. But we do have m dot 1 is the same as m dot 2 is called m dot hot. M dot 3 is the same as m dot 4 equal to m dot cold. So we can say in this case m dot hot multiplied by h1 minus h2 is equal to m dot cold multiplied by h4 minus h3. And this is the energy equation. We said most of the cases we want to have external heat transfer, but in case if we do have external heat losses from the system, just we can add heat here. Okay, so this heat if we do have external heat transfer. Otherwise, we do have m dot hot multiplied by change of enthalpy of hot fluid equal to m dot cold multiplied by the change of enthalpy of the cold fluid. Type if we consider for the heat exchanger, the last equation for the heat exchanger. If we consider actually, we need to calculate the heat lost from the hot fluid to the cold fluid. In this case, which is called actually Q dot hot. This Q dot hot, the heat lost from the hot fluid equal to m dot hot multiplied by H2 minus H1. The heat absorbed by the cold fluid, Q dot cold equal to M dot cold multiplied by H4 minus H3. This is in case if I need to calculate the heat transfer from the hot fluid to the cold fluid, or the heat transfer from to the cold fluid, which is equal to M dot cold multiplied by H4 minus H3. For the cold fluid, it is heated, so H4 is greater than H3, so this heat transfer will be positive as it is added or absorbed. For the hot fluid, equal to H2 minus H1, H2 is less than H1 because its temperature is reduced. So Q hot, this sign will be negative because actually the heat is lost from the hot fluid. The last steady flow device we are left with is the general flow in pipe and duct. So the last steady flow device, which is the general flow in pipe and duct. Okay. So when we do have flow in a duct or something, like actually all pipeline system, any pipeline system, in some cases actually we need to seal this system, or to keep it warm or something we can heat it using an electrical heater. So maybe we may have actually electrical heat input. If it is insulated, we don't have heat transfer, but in some cases the system may allow for heat transfer. In case of mixing, this is something very general in any application. In some cases we need to mix a fluid or something, so we may add paddle wheel. So in this case we do have shaft to power input to this power with paddle wheel, so we do have work input to the system in this case. So anyway, let's consider a system. Maybe in the case of air dryer, we do have a fan that forces air to go through an electric heater, so it heats up the air, or the case is reversed. So we'll consider the general flow in pipe and duct. So we may have any kind of heat transfer or adiabatic, or we may have actually any kind of work. So we'll consider the case actually as given to you. So we can apply the steady flow open system general energy equation and also mass equation. So mass equation will be M dot rho 1 A1 V1 is the same as O2 A2 V2 equal to density multiplied by volumetric fluid. The energy equation will be Q dot minus torque dot equal to M dot multiplied by H2 minus H1. In this case, we do have the same duct area, same cross-section area, same elevation, so the changing kinetic and the changing potential energies are neglected in this case. And this is actually the general pipe and duct flow. So the second case for open system, which is very important, which is the unsteady flow open system. Unsteady, we are considering mainly two cases. We do have two main cases. Either we do have a tank to be filled from, let's say we do have a flow or something, and we are actually to fill this tank with a certain fluid. So in this case, we do have mass. Let's say this tank is containing initial mass of this fluid M1. After filling this tank or something for a certain time, so the final mass will be, let's say, M2. Okay. So this is called a charging process. So the unsteady flow, either we do have a charging or filling process, or we do have discharging process. We may have actually both of them when we do have mass N is not the same as mass L. But most probably we'll do have one of the two cases, either a charging, filling a tank, or discharging. We do have a tank is a discharging flow. Let's say this is M1, initial mass, the final mass is M2. So if you apply the mass equation, it will be just M mass N, the total mass to the system, minus mass out equal to the change of the mass, which will equal to final mass M2 minus initial mass M1. So the mass N is the inlet mass to the system, mass out is the mass leaving, M2 is the final mass, and M1 is the initial mass within the system. If he said actually the system is initially evacuated, so this means actually M1 is equal to what? Equal to 0 in this case. If it is initially evacuated, otherwise it is there. Type mass in is a mass inlet to the system. If we do have a tank that is to be filled, then we do have mass in. But in this case is equal to mass out is equal to 0. Type if we do have discharging, a tank is discharging flow. In this case we do have mass out. But in this case mass in is equal to what? Equal to 0. So the general case that will be written is mass in minus mass out equal to the final mass M2 minus the initial mass M1. Type this is regarding the mass equation. Type let's consider the energy equation. I will just actually write the total form of the energy equation. It will be Q minus work equal to summation of mass exit multiplied by H exit plus V exit square divided by 2 plus GZ exit minus summation of mass inlet multiplied by H inlet plus GZ inlet plus, please don't forget M2 U2 minus M1 U1, which is a change of energy of the system. I am not proving actually this equation here, but just this is the general equation. Okay, those two terms usually neglected. Either discharging or charging or discharging. Now in case if we do have a charging or filling a tank, in this case we do have mass in, but in this case this term will be what? Will be 0. So this term is 0 in case we do have a charging process. Type this term, the whole term actually. Okay, type this whole term also will be 0 when we do have discharging process. A tank to discharge flow, so we do have mass out but we don't have mass in. A tank to be filled, we do have mass in but we don't have mass out, so this term, either of those two terms will be neglected in those cases. Heat transfer and work is the same. You have to consider sign conversion for heat transfer and work. If the system is adiabatic, heat transfer is equal to 0. If we don't have work not given or required, so in this case the work will be 0. The term of kinetic and potential energy will be neglected. So in this case will be given to you actually the initial condition B1, T1, then you can just go and calculate H1. Given the final condition B2, T2, then we can calculate H2. Type what about H exit and H inlet? In case of discharging we need to calculate H exit, in case of charging we need to calculate H inlet. In case of the working fluid is steam, this condition will be given B inlet, T inlet, or any other two properties. In this case, in case of steam, just we can calculate H inlet using table. But in case of air or something, or any other working fluid, gas or something, so in this case, if the condition are not given, just we will be calculating average temperature, which is T1 minus T2 divided by 2, and just go to tables. This is for gases from A17 up to A25, then we can calculate Hn or H exit, anything. Either discharging or charging, calculate the average temperature between the initial and final stage, then you can just go to the table to calculate the enthalpy. And that's all actually about chapter 5. You can just look at the slide, and the first comment also find the slides so that you can check the example solved on this slide, and also you can practice the other problem from the book. Okay.